Today we're going to talk about waves. This is an introduction to the concept of waves. And there are really three types of waves that we try to talk about. The first type are mechanical waves, and the second type um, are electromagnetic waves, and the third type are matter waves. And so mechanical waves are disturbances in some sort of physical medium. These would be things like water waves and or a sound wave, where it's a physical disturbance in air. The um, electromagnetic or E&M electromagnetic waves are light and all the things associated with electromagnetism. These are disturbances in an electromagnetic field. And the third type are matter waves. And these are things like um, the wave that governs the travel of electrons. So these are quantum mechanical, and we will wait and deal with this when we're dealing with quantum mechanics. Today we will be talking about waves in general, properties that are true for all waves, and in the next few weeks we'll be talking specifically about mechanical waves. We will then later in the year talk about electricity and magnetism and quantum mechanical matter waves. It's important though that we understand the generalities of waves so that when we come back to those topics, you're not trying to learn two things at once. You're not trying to understand waves as well as the quantum mechanics or the electricity and magnetism. So we usually classify waves as two different types. There's transverse waves and there are longitudinal waves. Um, the major difference between the two is how the medium or the displacement of the wave itself varies compared to the direction of travel of the wave. So for example, if you imagine water waves, if this is the surface of the water, as a water wave passes by, the water molecules right here below the surface, they move up and down as the wave moves by. If you've ever imagined like seeing like a buoy or a bird sitting on the water, as the wave moves by, the buoy slides up and down vertically as the wave crest moves by. And so the wave is traveling here in this diagram to the right, but the water itself is not moving up and down to the right. The water is simply moving up and down. Uh, this is like when you're swimming in the ocean. When the wave comes by, you ride up, you ride down. You don't get swept along with it unless you're attempting to ride a breaking wave, which we're not talking about. So that's the example of a transverse wave, something like a water wave. A longitudinal wave is that the motion of the medium, for example, air to make a sound wave, as the wave travels to the right, in this case, the individual air molecules are sliding back and forth in the direction of travel of the wave. Here you can see how a longitudinal wave is moving. If we watch one little particle here, so for example, watch one dot and follow it with your eyes. Don't take your eyes off of it, and you will notice that that one dot just slides back and forth to the right and to the left. It does not continue down the line. You can see that red dot in the middle is sliding back and forth to the left, even though the wave itself is traveling continually to the right. This is an example of a longitudinal wave. If I scroll down here, we see what's happening in a transverse wave. You can see the dots are sliding up and down. Watch one dot again, and you'll notice that it does not travel with the wave. It's moving perpendicular to the wave. This is the major characteristic between a transverse and a longitudinal wave. Waves can be much more complicated than simply longitudinal or transverse. Here we see a diagram of a legitimate water wave model, and because the water has a bottom, instead of being able to oscillate freely, the actual particles on the surface are moving more in a sort of an elliptical path. We're not going to talk about the mathematics of more complicated waves like this. But you should understand that the real world doesn't always have perfect wave behaviors. It's usually a combination of the two types of waves in a much more complex and real setting. Waves are described by a variety of parameters. The primary ones that we talk about are frequency, wavelength, amplitude, and phase. These are all pieces that appear in what is known as the wave equation. So the general wave equation for a transverse wave is y of x and t, and we'll explain each of these terms as we go, y sub m times sine of kx minus omega t. This term, y sub m, is known as the amplitude. This is the maximum height of the wave. That's known as amplitude, how big the wave can be. The frequency of the wave, or how often it oscillates in a period of time, is represented by this omega. This is known as angular frequency. And if you're familiar with the term frequency, they're related to each other by a factor of 2 pi. So this is how often this thing completes 2 pi radians of rotation. And we'll see later why we're in radians per second. The linear frequency, which you're probably familiar with, is number of oscillations per second. So that would be measured in a unit called hertz. So for example, a note on a piano might be 440 hertz. Well, the mathematics, the physics equations are generally written in terms of this angular frequency omega instead of the linear frequency f. The relationship is fairly simple. The k is known as the wave number. You can think of this as how, if you stood in one place and watched a wave go by, if you started counting when you first started watching, that first wave crest that went by would be 1 and then 2 and then 3, and then as you work your way down, you're farther down the wave. That's what is represented in a way by k. It's how far down the wave you're beginning to watch, or where you currently are on the wave. So you can either watch waves go by you or you can travel with waves. And so these two terms together, the entire kx minus omega t, determines where you are on the wave. So this entire thing determines where you are on the wave, and we refer to that as the phase. This is where you are inside of that sine wave. So if we graph this, you'll notice that this is going to look like a traditional sine wave graph. And so where we are, whether we're up or down a certain point. So if I'm right here on the graph, how do I know I'm there? Well, I can be there for two different reasons. If I have a snapshot picture of this graph as it's traveling by, I might be there because I'm a distance x away from the origin. Or if I was standing there and watching this wave travel by, I might be down at this location because the wave has traveled for a period of time that has made this point reach somewhere down on my x equals 0 axis here. So the phase is where we are within a wave, and I'll try to find a picture or a graph of how that is demonstrated. So omega, the angular frequency, is related to the linear frequency, is 2 pi f. And the wave number, k, is related to the wave length by this relationship. Lambda, this is known as wavelength, and is characteristic of if you start at one point on a wave and you travel and you start moving over, measuring distance until you get to that same point on the wave again. So in this case, high point to high point, or I could have gone low point to low point, or I could have gone place for it first crest crosses the axis going down to where it crosses the axis going down. That distance is referred to as wavelength. Those are the characteristic pieces of this equation, which we call the wave equation. Anytime that we end up with a mathematical solution that looks something like this, it's going to turn out that the motion of that system will be wave-like. We will find that solutions come out like this to much more complicated equations, like the electromagnetic equations that of Maxwell's laws or the Schrodinger equation of quantum mechanics, produce solutions that have a similar form as this solution. So we know that everything we learn about how water waves and sound waves travel and behave, we can apply to some extent to our understanding of electricity, magnetism, and matter waves. We'll continue with more about traveling waves in the next session.